My name is Dan Driscoll. I'm from the University of Washington. I'm going to talk about BlackParrot. We're announcing our new Agile open source RISC by Multicore. And we're designing it as a host core for accelerator-based SoCs. This work is done between Washington and Boston University. So the kind of motivation here is that traditional hardware design methodologies usually rely on proprietary tooling and proprietary IP libraries that don't promote reuse and are not accessible to hobbyists or researchers. But at the same time, new open source CAD tools and open source libraries are providing a way for hobbyists and researchers to get involved in this ecosystem. But it's no coincidence that this is happening in an era where diverse workloads require custom silicon. Accelerators allow us to continue getting performance gains while traditional transistor scaling is kind of petered out. But while custom accelerators are the secret sauce for these new systems, they don't stand alone. You need all sorts of components like the uncore, I/O, chip testing capabilities in order to maintain your own infrastructure just to develop a small accelerator to do a specific fixed function task. And getting any of these components wrong can completely destroy all of your accelerator gains. So general purpose host cores are needed to coordinate all of these accelerators, all these moving parts, all these uncore systems. But when you're adding a new host core to the system, there are several considerations. You want it to be efficient, performant, and reliable. It needs to be able to do what you want in your power and performance envelope. It needs to be able to control a diverse set of accelerators, both with standard and custom interfaces. It needs to be trustable. It needs to use standard design principles, standard design methodologies, standard design languages, so that people can just look at it, inspect it, and know that it's quality. And the IP needs to be extensively verified. If you have to do this redesign and re-verification, you've lost all your benefits of reuse. And last, it needs to be free and open source. You need to be able to play around with this and understand if it will fit into your system without purchasing a license or signing restrictive NDAs. So you end up just being able to click in an accelerator. This is the ideal case. So in order to fit this niche, we developed BlackParrot. We call it a base class for accelerator SoCs because we envision people taking the code, extending it to their own circumstances, and then contributing back so that other people can reuse it. We've designed the architecture to be flexible enough to allow for this extensibility, and we've released the code under permissive BSD license. But we don't want BlackParrot to be the best core on the market. That's not our goal. Our highest performance core, rather. We want BlackParrot to be small, efficient, and obtrusive. We want it to be able to go in as many systems as possible without dominating the performance or area, restricting performance or dominating the area. So on our route to going global, we measure our progress around 4 distinct axes. We have quality. Will people trust the code? Will people be able to justify putting it into silicon? Will people be able to use it everywhere? Will it fit into all use cases and be able to use all accelerators with it? Does BlackParrot have everything that you need? Can it do all the general purpose code and host all the kind of accelerators that you want? And just as importantly, does it have a minimal set of features? Unused functionality in silicon takes up power and area, and most importantly, it adds complexity, which increases verification costs. And lastly, is it efficient? Does it do what you want in the power performance envelope that you need? So this is kind of the design principles that we've come up with for BlackParrot. When we try to add a new feature, we consider these 3 factors. We try to be tiny. We want to have a small code base and small design so that it will fit as many places as possible, and also so that people can wrap their head around the code, be able to go into the code base and be able to find issues without having this kind of overwhelming part of this overwhelming code base. We try to reuse open source libraries like Basejump STL, Google RISC IBB, Berkeley Hardflow, things that are well verified and well documented so that people can come in with their own experience and be familiar with the BlackParrot code base. We also want to be modular. We want people to be able to modify only a small part of the code and be able to make their own changes without having to verify other parts of the system, have these cascading effects that are extremely difficult to debug. And last, we want to be friendly. This kind of means, as engineers, we want to reinvent the wheel all the time because it's super fun. But it makes more sense to reuse libraries that exist, reuse code, and avoid non-invented here syndrome as much as possible. So that's kind of setting up the stage of why we developed BlackParrot and what our design goals and methodologies are. Now we'll talk about the system architecture, kind of this uncore component that makes it really easy to integrate Accelerator into our system. And I want to note, we're not trying to develop a SoC generator. Our role here is more to provide a reference SoC methodology and a bunch of building blocks that people can use to plug in their own accelerators into BlackParrot's SoC or integrate BlackParrot SoC components into their own system. So in our system, BlackParrot comprises of 3 nodes. There's what we call the Bedrock network for managing coherence transactions, the I/O network, which manages off-chip communication, and the memory network, which manages DRAM communication. These are all connected via wormhole routers, which are small, efficient, and fairly easy to verify. And we use regularized tiles to make sure that it fits into a normal hierarchical pad flow. So I mentioned Bedrock. This is our fully cache-coherent multi-core infrastructure, which allows traditional messy-type coherence using a novel protocol. This protocol divides the system into 2 components: local cache engines, or LCEs, and cache coherence engines, or CCEs. The interesting thing about this is that CCEs have all the actual protocol information. Local cache engines only respond to very simple messages and have limited shadow state knowledge of the entire system. By doing this, we can eliminate all transient states during the protocol, which makes it vastly simpler to verify. So now we'll take a look at the sample BlackParrot SoC. This is kind of the reference with all the bells and whistles that you can make with the BlackParrot SoC. It turns out we can separate BlackParrot tiles into 4 distinct categories. Core tiles are the most basic type. A single coherent core of a BlackParrot multicore, along with uncore components needed to communicate with the rest of the system. Streaming accelerator, or I/O tiles, do not cache coherent memory. Instead, they stream data to and from the core. Now, this could be something like a GPU or a fixed function accelerator, which does the DMA. There's also coherent accelerators, which do fine-grained communication between the core and the accelerator cache coherent memory. And this is useful for cooperative workloads. This is an interesting part of BlackParrot because you're able to have cores and accelerators very fine-grained communication. This introduces a whole class of SoCs that people can develop. And last, we can extend the memory of the tile throughout the system, using L2 extension tiles, extending the distributed L2 and providing more directory tags and L2 cache, which allows you to change your memory to compute ratio for a specific application. Now we'll zoom into a BlackParrot core tile and look at the uncore components that make it really easy to do. So core tiles kind of have everything that you need, and you'll see a lot of these components repeated in all the other tile types. These tiles connect with base jump STL wormhole routers. This is leveraging an open source library. We don't maintain the code for these routers, so we're able to keep our code base lean and narrow. There's also wormhole concentrators, which allow all the components to talk through one router. There's a CCE, which manages directory tags and the coherence information for a slice of memory in the system. So all the cores are able to request data from this one CCE, which serializes all the protocols. There's also BlackParrot's deeply integrated L1 caches and distributed L2 cache, which provides fast performant on-tile memory. And last is the actual BlackParrot core logic. And this is the only custom logic in the tile. Everything else here is reused with other components. In fact, anyone who has their own RISC-V software, please come talk to me after this. We'd love to integrate more cores into the BlackParrot family. So now we've looked at the uncore components for a BlackParrot tile. We'll look at how to compose other tile types in the taxonomy. L2 extension tiles maintain the coherence directory tags with a standard CCE, but packet the rest of the area with L2 cache. So you basically just rip out the core, but reuse all the rest of the memory in the tile. Coherent accelerator tiles have a standard LC, but a simpler version of the CCE, which only manages configuration data, scratchpad memory, and local on-tile memory that is not coherent with the rest of the system. Streaming accelerator tiles reuse this minimal CCE, but have no need for a coherent LCE. Instead, they communicate over the I/O network or simply stream results back and forth with the rest of the system. And even among these accelerators, BlackParrot has several different levels of integration logic. that you can have. Because all the true coherence state is managed by the CC, as long as you have a CC attached to the Bedrock network, you can have LCEs that have different types of components seamlessly integrated without having to write any custom coherence logic. For a stream accelerator, the stream accelerator only needs to generate command and response requests, which could be used over any standard memory protocol. In order to attach a coherent accelerator, the designer can reuse BlackParrot's LCEs and data cache, and only have custom accelerator logic for the actual accelerator fixed function logic. If a designer wants more control over the specification, they're able to use completely custom cache and reuse BlackParrot's LCE, just reusing this standard cache service interface that we've defined. And lastly, designers are free to implement full custom accelerators, which obey the simple LCE functionality required by the Bedrock protocol. This option offers the most flexibility, but it has the trade-off of longer development times. We've developed this to be so modular, however, that you can start with your custom accelerator and standard BlackParrot cores, and then one by one go down the stack and customize to get the best performance, maintain testability of each step. So now we've looked at the system architecture, we'll dive a little bit into the BlackParrot core architecture. This part of the talk is a little bit, this is the first version of the BlackParrot core microarchitecture. Because we define this as standard interfaces, you can seamlessly switch in and out these different core components without any impact on the system. So the BlackParrot core itself is a simple in-order pipeline, 8 stages with full forwarding FPU and non-blocking, non-stalling backend. Interestingly, the directory controller is not a standard FSM-based directory controller like you find in most message-based systems. We actually have a programmable cache coherence engine, which uses a custom RISC ISA to add functionality This gives you the flexibility to program different types of coherence traffic, such as security, functionality, and debug information, even after you've taped out into silicon. And all these building blocks, like I kind of working on, have these standard latency-insensitive interfaces. And we spend a lot of time making sure these interfaces are able to have a wide range of implementations on either side without impacting the functionality or timing information of other blocks. This is key to making sure that BlackParrot is a scalable development model, and people from all over the world are able to modify different components and able to integrate them together. So now we've talked about BlackParrot's design philosophy and system architecture. So we'll talk about how we're building a flock of users and developers around the project. First, we have our modular hardware compliance test suite. And this is driven by the insight that test benches are expensive, but tests are very invaluable. Developers are able to modify small systems of small components of the system and use these standard hardware interface compliance tests to make sure that their interface or their implementation is compliant with the standard interfaces. This testing structure allows BlackParrot to be confidently extensible with robust verification. We're trying to develop BlackParrot as an example of community-driven microarchitecture. Just as Linux has this global stewardship and distributed developer base, we want BlackParrot to be directed by the community rather than controlled by any single entity. The first method is recognizing that ideally BlackParrot's users will become its developers. We want to make it as easy as possible for someone to go from downloading BlackParrot to making their first pull request. We don't want people to have intimate architectural knowledge of the system to improve their small area of expertise. If you have a TLB expert, you don't want to have him or her to understand the branch predictor in order to modify it. Second is building a development infrastructure based on freely available CAD tools. This lowers the barrier of entry so that hobbyists and researchers are able to get started up and running with the system. And last is focusing on out-of-the-box experience. Users should be able to go from GitHub to simulation or even ASIC in only a matter of few clicks, without having to debug toolchains or install proprietary software. We've successfully run BlackParrot on Arctic 7 and Genesis 2 FPGAs. We're also diligently working to get BlackParrot into Linux, which is an FPGA, open source FPGA-based, open source Python-based FPGA design environment, which allows people to have their own FPGA and all the peripherals accessible by BlackParrot while we don't have to maintain any of the code in our central infrastructure. We're very excited for this because we don't want to maintain FPGA infrastructure, but we would love to get BlackParrot into the hands of all the FPGA users in the world. BlackParrot's also been taped out in an advanced 12-nanometer process node, with many more tape-outs on the way. This is a process-agnostic design which has been validated in several different techniques. And not only is BlackParrot's RTL open source, we also open source the tape-out directories that we use for taping out our chips. This is at github.com/BlackParrot examples. You can go today and look at our synthesis scripts, the timing constraints, different memory information, and all our BlackParrot tape-outs, past and future, will be hosted there. We're also hoping that anyone who tapes out BlackParrot outside of our group contributes to that repo, so that we can share these insights of how to get a very performant SoC to our quality of results. We also participate in the Open Road CAD flow, which is free and open source, 24-hour push button CAD flow, brand new, being developed right now. And this allows you, using Open Road BSG Figbrand through PDK 45, to push all the way through an open source CAD flow today. This is a picture of BlackParrot Genesis release date. And we say Genesis release because we view our role as bootstrapping the development movement rather than becoming stewards of the code ourselves permanently. We don't want to throw BlackParrot over the fence every 6 months, have people fork it and have it to their own needs, and then never contribute back, and have this kind of central, agreed-upon, standard post-work world. We want this Linux-like development model where everyone works on the same code base, and people are able to parameterize it enough to fit their own specific use cases. So I presented BlackParrot, the landscape diversified multicore. It's silicon validated and ready to be included as a host core in your next Accelerator project. If you want to build up the BlackParrot user base, please use and explore, break things, raise issues, pull requests. We're looking for particular help with porting benchmarks. We need a lot of help on the software side, just person power, and porting to various FPGAs. Different development environments are interesting to us. We'd love to see bugs, or I'm trying to debug us a new Ubuntu 14.n. We're also looking to integrate BlackParrot with any novel accelerator system that you have. So together, please come talk to me if you're interested in working with us. We can make BlackParrot the global default choice for RISC-V for us. So thank you.
Yeah, you have like a minute and a half to do a question if you want. Okay. I think the next person can go.
How many contributors have you got outside of the 2 universities?
You have to repeat it because we don't have them.
Oh, sure. The question was, how many contributors have we had outside of 2 universities? So BlackParrot's kind of developed collaboratively with FaceJump STL. We have many outside contributors to FaceJump STL, and we've had issues that have been raised in BlackParrot that have been fixed there. BlackParrot itself, we're trying to build up this community more so. Any other questions?